Gina Duggan. I'm a grad student at Caltech working with Evan Kirby. And so I work on dwarf galaxies, specifically measuring dwarf galaxy abundances, and specifically barium. And so I'll talk a bit about my recent paper that came out, but the main focus of this talk is my next paper, which is about galactic chemical evolution modeling to match the observations that I have observed. So in the background of my title slide, I have Sculptor Dwarf Galaxy, which I'll talk about a lot during this talk. And as Mohammed mentioned, the goal is to figure out where our process is occurring in dwarf galaxies. And specifically, I focus on early times in dwarf galaxies, so before a metallicity of about -1.6. Okay, so we'll start out with a bit of a cartoon talking about galactic chemical evolution. So here's a cartoon galaxy where the gas is shown. And so the important processes that drive galaxy evolution are obviously, you start out with the gas in the galaxy, and then stars are formed out of and they adopt the chemical composition of the gas of when they were born. Then at the same time, we have primordial gas inflows, which dilute the heavy elements in the galaxy's gas. We have stars, either through winds, mergers, or explosions, enrich the gas in the galaxy with heavy metals. Sorry. And in the case of explosions, this also creates a galactic wind, which has a gas outflow out of the galaxy, and so you lose those metals. And so you can't watch all of these different processes happen in real time, so I use galactic archaeology to see this. And so galactic archaeology utilizes the fact that long-lived stars adopt the chemical composition of when they were born to look back through time and see how this evolution occurred. And so to do this, I trace a variety of elements. Specifically, I trace alpha elements, which is created through core collapse supernovae. And alpha elements have a very short delay time. And by delay time, I simply mean the time between a star being born and a star ejecting enriched material into the ISM. Then we have iron. Iron's created by both core collapse supernovae and type 1a supernovae. And type 1a supernovae have a very long delay time, described by a delay time distribution. And then we also have elements heavier than iron. And so these elements, heavy elements, are formed through neutron capture processes. And the origin is unknown, and the delay time, therefore, is unknown. And so that's what I'm going to talk about today, that the key to figuring out the origin is actually figuring out the delay time. And so alpha to iron is commonly used as a chemical clock in many different systems. And so here's a little diagram of this. So if you start out with the star formation history in the top left, you can convert this into iron versus time. And so you do that through assuming an IMF and then assuming iron yields from supernovae. And then you can convert our observable, for example, magnesium to iron as a function of iron abundance into the contribution of core collapse to type 1a supernova as a function of time. And so this starts out, this ratio magnesium to iron, and magnesium's an alpha element, it starts out very high because core collapse supernovae explode very quickly. And then as type 1a supernova kick on, it drives down this ratio. And so my work is not only using alpha to iron, but also using a neutron capture element, barium, to iron as another type of chemical clock. And so in this little model here, I have barium predominantly produced by AGB stars. And so this ratio, barium to iron, probes the contribution of AGB stars to type 1a supernova as a function of time. You can also use barium to europium, which is two different neutron capture elements, which have different ratios of being created by the R and S process. And so this ratio helps you determine what percentage of neutron capture elements is coming from the R or the S process as a function of time. And so here's our definition of the R and S process. So the S process is the slow neutron capture process, and then the R process is the rapid neutron capture process. And so these two different processes are created in very different physical scenarios, and therefore from very different astrophysical origins. And so the slow process happens quite slowly, as you can imagine. So the neutron capture timescale is 10 to 10,000 years. So that's the timescale between the atom capturing a neutron, and that's much longer than the timescale for that neutron to decay into a proton through beta decay. And so it follows the value of stability, and the S process occurs in episodes lasting from 100 to 10,000 years, and at least for barium, predominantly is produced by AGB stars. The R process, in comparison, neutron capture timescale is very short, so 1/100th to 10 seconds. And this is much shorter than the beta decay timescale. It occurs in seconds, and as you see in our list of astrophysical origins, it is, we expect it occurs either in explosions or mergers, or some combination of the two. So the origin of the S process is very well known and has been studied for a long time, but the origin of the R process is still up for debate, and that's the main topic of this talk. So one possibility is core collapse supernovae. And so we'll discuss typical core collapse supernovae first, which is shown on the slide right now. And then we'll talk about magnetorotational supernovae, which is one of the rare types of core collapse supernovae that could produce a lot of our process. So I've shown here simulations by Wanajo et al. 2013 of a typical core collapse supernovae. And what I want you to take from this is that except in the highest masses of the proto-neutron star, barium is not produced in a average core collapse supernovae. And then on the right now, we have the simulations of a rare magnetorotational supernovae. And so this is expected to be 0.1 to 1% of core collapse supernovae, and has very high magnetic fields and or rotation, where the R process would occur. And so, as you see in this simulation, they are able to produce the full R process pattern. And so these simulations present magnetorotational supernova as a viable source. Other people have mentioned collapsars, which all would have a similar delay time distribution. So a very short delay between the star being born and the star ejecting this enriched material. So then we also have Neutron Star Mergers. And so here's a simulation by Code et al. 2017. And as you can see, it's able to produce the full R process pattern. And so to summarize, for barium, we're considering AGB stars, and then magnetorotational supernovae, and or neutron star mergers for the R process. And so the main observational difference between these rare types of core collapse supernovae and neutron star mergers is the delay time. And so this is because both simulations are actually quite flexible and are able to produce large amounts of our process. So the main observable difference is that magnetorotational supernova would happen very quickly and neutron star mergers would be more delayed. And that's the signal that my research is sensitive to. Now, I can't talk about neutron star mergers without mentioning, as you all know, a bit over a year ago, the first neutron star merger was detected, and our process yields were determined to be actually quite high from this event. And I noticed that you all had a talk in November about this source specifically. So, so my work is using the chemical evolution to determine the nucleosynthesis sites. And the things you need to keep in mind are the enrichment timescale, our process yield per event, and the rate per event. And I argue that this is most easily seen in dwarf galaxies. So this is because the chemical enrichment of galaxies help distinguish by the continual buildup of our process events rather than looking at single events. And dwarf galaxies offer a unique opportunity to study the astrophysics driving galaxy evolution because their small masses make them very sensitive to feedback mechanisms. The lack of major mergers enable detailed studies of chemical enrichment, and the small sizes result in nearly instantaneous mixing within the galaxy. Now, dwarf galaxies have already proved extremely useful in the case of Reticulum II, which I've shown here. So this is a paper by Alex G et al. That came out a couple years ago now. And so what we're seeing here is barium dihydrogen on the left as a function of iron, and then europium dihydrogen as a function of iron, and then the pattern, which shows that the enrichment that we see in these stars is from the R process rather than the S process. And this is evidence, this hints at what I mentioned earlier, that the ratios of neutron capture elements can help determine whether it's from the R or S process. And so what Alex discovered was that a group of stars in Reticulum II, shown in bright red, have elevated barium and europium compared to all the other stars measured in the other ultra-faint dwarf galaxies. And so this, because we see this signal in Reticulum II and not in the other ones, it's an example that this is a rare event. And the magnitude of the increase implies it has a very large R process ejecta. And so the conclusion of this paper was that there was one big event that contributed our process, which was very important because the other idea that has been considered for a long time is that a typical core collapse supernova would eject small amounts of our process and it would gradually build up. So now, in addition to the simulations saying that this is unlikely, we have observational constraints saying that that's not the only source at the very least. However, because it was a single event observed, you can't distinguish whether it was by a neutron star merger or a rare type of core collapse supernova. And really you need to observe many R process events in order to tease out what the typical timescale of this R process enrichment. And so we have looked at this by looking at the abundances in 5 different dwarf galaxies with a variety of masses and star formation histories. And we use my barium measurements that were published last month, which was the largest sample of barium measurements in dwarf galaxies to date, with a total of almost 250 stars. So here we are discussing the sample that I'm using. So right now I have shown the current published measurements as of December. And so this is from mainly high resolution studies. And I have now overplotted my sample of barium abundances using medium resolution spectroscopy with DEMOS on Keck. And so this is very exciting because it means for the first time, we're really able to look at the abundance trend as a function of metallicity for many different dwarf galaxies and kind of see what we can tell. So just a reminder, we're talking about using barium to iron as a function of iron as a chemical clock. And right now I'm going to transition to talk about how can we distinguish barium produced by the S process from barium produced by the R process. Because in order to study the trend of R process enrichment, I need to be able to isolate the R process enrichment. So we're using this ratio of barium to europium as a function of iron. So here on the left hand, I have stacked the barium to europium as a function of iron for 4 different dwarf galaxies. And so here I've plotted all the literature detections of barium to europium, at least published by last month. And I have fitted linear trends to this measurement. And so my sample doesn't include europium because their lines are very weak and difficult to measure. especially with medium resolution spectroscopy. So we have turned to the literature to help us out. And so, so on the right, you see this conversion. So on the x-axis, we have barium to europium values, and on the right, on the y-axis, we have the fraction from the R process. And so using these linear fits, I've then converted what fraction of bariums from the R process to then only look at that component. And so that's what we're looking at here. So this is a complicated plot. On the left-hand side, we have the stacked magnesium to iron as a function of iron. And so this is from a Kirby et al. 2011 catalog. And then on the right hand, we have the barium to iron only from the R process. So I've already subtracted the S process out for, again, the same 4 dwarf galaxies. And so what we're doing is we're comparing the chemical trends of alpha to iron to barium to iron for the same galaxy. And so there's a lot of strength in this because that means that we're taking into account effects of the star formation history, the gas inflow rates, and all of that is the same between the alpha to iron and barium to iron from the same galaxy. And so, so if we consider if the R process barium contribution is from core collapse supernovae or a rare type of core collapse supernovae, then we would expect to see a similar barium to iron trend. And so if barium's being contributed by a core collapse supernovae, it would be contributed, it would have a high value early on, and then as type 1a supernova would go off, this ratio would decline. However, in red, I've now plotted the fitted abundance trend, and we observe a much more positive barium to iron slope than magnesium to iron for the same galaxy. And so the numbers in the bottom left is the number of the slope with the errors from fitting this data. And so what you see is in every case, the slope at early times is much higher in barium than in alpha to iron. And so this means that we in fact do not have the dominant source of our process coming from core collapse supernovae and need to consider more delayed barium enrichment. And so we know it's not AGB stars because remember we're plotting just the R process component. So we've already subtracted out the contribution from AGB stars. It's not type 1a supernovae, even though the delay time would make sense because they don't produce our process. And so we consider neutron star mergers as the most viable candidate. And so again, we need a delayed contribution because a positive slope, which is most clearly seen in like Ursa Minor and Draco, is that as type 1a supernovae are contributing large amounts of iron, we're still getting a significant amount of barium contributed in order to get this positive slope. And so this was the main result of my paper published last month.
So Gina, what about the sculptor? Why is the slope negative there?
So for Sculptor, it's actually interesting. So we've fitted 2 different lines because the trend in Sculptor seems to have a turnover at around metallicity of -1.6. And so if you look at the red line fitted at earlier times, it is still, while it's still slightly negative, it is significantly more positive than the alpha to iron slope. Because alpha to iron slope for Sculptor was -0.69 plus or minus 0.06. And for barium to iron, it's -0.21 plus or minus 0.17. So I would argue that it's still significantly more positive than if it was dominantly produced by core collapse supernovae.
So you just are saying that, so you don't require the BA over FE to have a positive slope. You only require that it has a more positive than slope than mg over FE. You don't care that if the absolute slope is positive.
Mm-hmm. Yeah, that's absolutely right. Because if it's a more positive slope, it means that there's some contribution occurring at a similar time scale as type 1a supernovae. It might not be sufficient to overpower the iron coming from type 1a supernovae in that galaxy, but
So
we're not seeing.
so what would explain the fact that it is still negative? So you're saying that there hasn't been enough neutron star mergers happening in Sculptor?
Yeah, or that the type 1a supernovae contribution is dominating over the barium enrichment.
Okay.
Yeah, so that would be the argument here for Sculptor. And as I said, Ursa Minor and Draco is a much more dramatic evidence. Right, so that was the kind of a more qualitative explanation for why we believe neutron star mergers are extremely important R-process contributor at early times in dwarf galaxies. But now I want to transition my talk to talk about using a galactic chemical evolution model in order to kind of more quantitatively determine what this contribution from neutron star mergers might be and why it is so important. Are there any other questions about this part of the talk?
Sounds like you can continue.
Okay. All right. So again, we're going to use a galactic chemical evolution model to quantify the enrichment. So our galactic chemical evolution model has a very short computation time to allow for careful determination of the parameters through Markov chain Monte Carlo analysis. And so here I have, again, our little diagram, and I've drawn a box to demonstrate that it's a one-zone model, not that it's a closed box model, because it's not. And so our model tracks the total gas mass of the galaxy as a function of time. And so we start out with a free parameter to define the initial mass, gas mass of the galaxy. Then have stars form out of that gas using Kennicutt-Schmidt law. We have a primordial gas inflow, and the functional form of the gas infall rate was chosen to match the smooth rise and fall of the metallicity distribution function. We then have gas outflow from supernovae and gas yield coming from AGB stars and supernovae, and then later on I'll consider neutron star mergers. And so to remind you kind of how this works, so you have a star formation history. From the IMF, you can determine the occurrence rate of type 1a, type 2, and AGB stars. Then from yields, supernova yields specifically, you can convert time into iron abundance. And then you can use, you can create these abundance trends and actually iteratively fit them with the observed abundances. And so again, in this model I've shown here, the barium is predominantly coming from AGB stars. However, when we first ran this model, we noticed that while the parameters that we put in matched alpha to iron, it did not match the barium to iron, which is again seen on the right. In fact, our model was underpredicting barium to iron significantly from 0.5 to maybe even almost 1 dex. And so then we started stepping through what are the possible areas that we could tweak our model without adding neutron star mergers to kind of fix it so that it would simultaneously match the alpha to iron and the barium to iron abundances. So first, we considered our star formation history. And so here I have 2 different star formation histories that we considered and their impact on the abundance predicted. And so this is a fairly dramatic change in the star formation history. And even then, it isn't able to get barium anywhere near where it needs to be. And so the star formation history is constrained by the HST color magnitude isochrone fittings. So we have star formation histories. And so in order to retain a physical star formation history, we are unable to get the barium where it needs to go just by altering the star formation history. So we turned instead to look at AGB stars. And so here I have two different AGB yield models multiplied by a factor of 2 and 3. And so this is just kind of to see if I crank up the yields of barium from an AGB star, can I recreate the observations? And so my conclusion is no. Not only if I kept cranking up the yield, perhaps I could get this forest of lines to match the observations, but I think we would have to crank it up to unphysical levels since these two different models agree within about these factors. In addition, as you can see, there's the AGB yields get a positive slope at late times, which is most easily seen in Sculptor, Ursa Minor, and Draco, and that trend doesn't match the trend observed in the barium abundances. Specifically in Sculptor, we actually see a flattening of the barium to iron trend at higher metallicities rather than an increasing trend.
So what is the yield you assume for neutron star mergers?
At the moment, this has no yield at all from neutron star mergers.
In the previous plot, when you were trying to explain it with,
this plot?
You wanted to change the yield from neutron star binaries to match the observations?
Oh, I haven't done that yet. So this is the, oh yeah. So I haven't added neutron star mergers at all into this model yet.
Oh, this is only from AGB.
This is only from AGB stars with a trace amount coming from core collapse supernovae.
Oh, okay, cool. Okay.
Right, so we have not added neutron star mergers at all. This is part of my build-up to show you why we need neutron star mergers. Oh, and then finally I wanted to point out that the AGB yield is able to match for Fornax, that green line, so the Caracas AGB yield times 3. But it's unable to simultaneously match Fornax and the other 3 dwarf galaxies. So now, this is my model including neutron star mergers. And so we are able to finally populate the barium to iron ratios that we observe. And so the line that I have plotted, I selected by eye. And so its yield is 1.4 times 10 to the minus 5 solar masses per type 1a supernovae. So as a preliminary step, I've modeled the rate of neutron star mergers, the delay time, not the rate, the delay time distribution of neutron star mergers to be the same as type 1a supernovae. In the future, I'm going to play with this delay time distribution a bit to see how strong an impact it has. But this is actually not a bad approximation because neutron star merger delay time distribution is very uncertain, and it's expected to have a similar shape as at least double degenerate type 1a supernova, since the time is dominated by the merger time of these two stars. And so here I have separated out the different contribution from AGB stars, core collapse supernovae, and neutron star mergers for the yield that I just showed, for the model I just showed. And then the total, and you'll see that in all cases except for Fornax, the contribution of barium is dominated by neutron star mergers. It also intuitively makes a lot of sense that Fornax would be more dominated by AGB stars because it has the largest period of star formation of any of these galaxies by a very large amount. And we see this rise at very high metallicities for dwarf galaxies, which we did expect was from AGB stars. And so that's a good check. Finally, to give you a kind of back of the envelope calculation to see if the yield that I fitted is feasible, if you start out with the type 1a supernova rate and multiply it by that yield of barium from neutron star mergers per type 1a supernovae that I mentioned on the previous slide, that gives you the total amount of barium that we are saying would come from a neutron star merger, or from many neutron star mergers. You divide that by possible neutron star merger yields, so 3 times 10 to the minus 5 to 10 to the minus 4, then you would get this neutron star merger rate. So it would be approximately 5 times 10 to the minus 5 to 10 to the minus 4 neutron star mergers per stellar mass per gigayear. And so if you compare this to the range of neutron star merger rates predicted, we are within the range. And so as you probably know, this is a large range from 10 to the minus 7 to 10 to the minus 4. And so that's where you can really see that we'll provide a very unique constraint on the neutron star merger rate and or yield. So the path forward is to constrain the neutron star mergers. So I will be implementing an MCMC fitting algorithm to simultaneously fit the galaxy properties and the neutron star merger contribution. And again, that will return the total mass of barium contributed by neutron star mergers per dwarf galaxy. And so using various models, I can constrain the rates, and various rates, I can constrain the yields. And so, here I am just overplotting the different models while varying the barium yield from a neutron star merger. So to conclude, using the largest sample of barium abundances in dwarf galaxies, we've discovered that at early times, barium in dwarf galaxies is created by a delayed R process source, likely neutron star mergers. And using new models, we have confirmed that neutron star mergers are the most likely physical origin. And so in future work, we'll use these models to constrain the neutron star merger rates and yields. Thank you.
Thank you, Gina. You can turn up your mic and your video and ask questions if you have.
Hi, Gina. Can I ask a quick question?
Yes.
So very interesting talk, by the way. I appreciate the looking for new things to look at to determine the source of our process. But if you go back to the figures where you were showing the model results without including neutron star mergers?
Yeah, with varying AGB stars, this one?
Yeah.
Mm-hmm.
So if you had something that produced a lot of barium at early times, you would essentially just push that line up. And so at least, I know the other stuff you looked at said that you need to have this delay time distribution, but just looking at these, if you had something produce a lot of barium at early times, like if you just cranked up the expected barium yield from supernovae, would that push those lines to be consistent with that data?
Well, so I just changed the slide to match. So I have done that. So I've cranked up the core collapse supernova yield, just kind of arbitrarily. And what you do see is you see a negative slope that, again, isn't observed.
I see.
So I don't think, and I think even if you combined, higher AGB yields than you think and higher core collapse yields than you think, then you would end up with a dip in the middle that we also don't observe. So I don't think that there's a way to use the core collapse to match the trends.
Okay, interesting. Thank you.
Mm-hmm.
Any other questions?
Yeah, if I could ask, what does your model say for Reticulum II? Is there any more information in that case?
I don't think that my models have much to say about Reticulum II, specifically because Reticulum II is a single event, whereas the strength of using larger dwarf galaxies is that you can probe the dominant trend, and so you have many different large R-process rich events that you can observe the average delay time difference. Whereas Reticulum II, given it's a single event, it's hard to say whether it was a rare type of neutron star merger that happened to go off very quickly while stars were still forming in Reticulum II, or if it was one of the rare types of core collapse supernovae. My work specifically doesn't rule out core collapse supernovae or even rare types of core collapse supernovae from being a possibility. We just argue that it's not the dominant source of our process in these dwarf galaxies, because otherwise we would see a different slope.
And then, like you seems like you changed the barium yield as well, like you crank it up 10 times. Is there no theoretical or observational bound on how much you can, or can you multiply by 100? I don't know, like what is the uncertainty on those yields?
On the, I don't know if I understand, on the neutron star merger yield?
Well, like right in this panel, you have cranked up to a factor of 10, the barium. I mean, is it consistent with theoretical expectations? Can you just
for the core collapse?
100 times? What is the bound?
For core collapse supernovae?
Yeah. For example, why did you stop at 10? Why didn't you go out higher than 10?
Well, so I stopped at 10 pretty much because you were seeing the trend in the slope. So like if you keep increasing it, I had hoped it would be obvious that the slope would just become more and more negative at low metallicities. You could, if it was magnetorotational supernovae, like that produce very large quantities but are really rare, I don't know the precise equivalent of how much you would pump up the yield from a typical core collapse supernovae.
But like, for example, what I see here is that if you, for example, don't stop at 10 times, and if you go to like 50 times, I don't know, then the line will go through the points, and then for the negative slope, there is no point to constrain there.
Well, it would go through, well, because like in Draco and Ursa Minor, I think we get to the point at the earlier part of the talk, which is the trend is much more positive, barium to iron as a function of iron. So yeah, you would get the line through the observations in the middle, but the trend would be a huge decline, which we don't observe. Because like even for Sculptor, if we pumped it up by an additional factor of 5, we have a bunch of stars at this that are increasing, and it wouldn't match any of the stars like below Fe/H of -2.
I see. And could you show the same plot that you explained this with neutron star mergers?
Yeah.
Instead of AGBs?
Yeah.
Oh.
Is this the one you were talking about? So this is where we're varying the contribution from neutron star mergers.
Right. I see.
And the sharp rise, is based off of the turn on of type 1a supernovae. And so at the moment, these models are assuming a Mauserdal 2010, where the turn on is at 0.1 gigayear. But if we use the more recent prediction, it would actually be much earlier, so 0.04 gigayears, which would probably capture the low metallicity Sculptor stars. And so that's another thing that we can.
The point is you're plotting like several lines, but all the several lines, each one of them go through part of the data points, but there's no single one that can explain every point there. And then, but if there is a neutron star merger happening, we have to pick a yield and it will give us one of these lines. And by eye, any of these lines that I pick, it would be hard to match the data. It's like the data is too much scattered in vertical direction.
Oh,
and if you do a KS test or something, I don't know if you can even accept the model. You know what I mean? Like, have you drawn, like, randomly sampled from that, however many data points you have, 100 data points, sample 100 data points from one of the models, and see if the KS test agrees that this is a good fit with any yield. Have you done that? I mean, by eye, collection of them go through, but we have to choose one of them.
Yeah. So by eye, I would argue.
Exactly. Is this a fit? Is it acceptable?
So no, I haven't done that test yet. I also want to mention, I think you're trusting the scatter in my observations much more than you ought to, because the error bars.
Even with the error bars, you can sample from your curve with the same error bars.
Yes, no, I know. I guess I was saying by eye, don't discount that there's a scatter, and so one line can't match the whole scatter. But the KS test should certainly be done when I do my fits, and so that's under future work. But I think that it's undeniable, at least with what I've shown you, that the neutron star mergers are the most promising out of the AGB stars and core collapse for where this barium is coming from.
Yes, absolutely. Any other questions?
I just wanted a clarification. This is Rick out in Arizona. You said that your delay time for your merger event was constant across all of these models. It was like 700 mega years. So there's no range you're pulling from. They're all going off in kind of a type 1A delay scenario.
Yes, so they're all going off with the Maus et al. Delay time distribution. And I have the functional form of that here, but pretty much, I assume the same delay time distribution for all of them. And it's, t to the minus 1.1.
Okay, yeah, thanks. T to the minus 1.1. Got it.
But in future iterations of this model, I'm going to alter which delay time distribution we assume.
Normally people use a power law for neutron star binaries. So.
Yeah, I mean, they use a power law of t to the minus 1, and this is t to the minus 1.1.
Yeah, that's what we use.
So it's a power law as well.
Oh, okay. Yeah, I see.
Yeah, it's interesting. It's basically the power law we used, Mohammed.
Yeah.
Any other questions? Well, if not, let's thank JINA again. Thank you very much, JINA.
Thank you.
And in 2 weeks, we will have some other speaker. We haven't decided yet, but soon we will have it. We'll decide that, and hopefully I see you guys in 2 weeks.
All right. Thank you, everyone.
Bye, JINA.
JINA.
Bye.